All right. Thank you very much. So let me begin by reviewing a little bit of what I talked about in the previous lecture. So FQ is going to be a finite field with Q elements, and I'm going to let Y be some algebrogeometric object which is defined over FQ. And so you could have in mind an algebraic variety over FQ, but a better model for what I would like to do is an algebraic stack over spec FQ, like the moduli stack of G bundles on an algebraic curve. And then you can look at the FQ valued points of Y. So if Y is an algebraic variety, this is just a set, in fact a finite set. But if Y is an algebraic stack, it's something that you should really think of as a category. And you can measure the size of this category in the following sense. This is a sum over the, let's say, the objects of Y of FQ. So here, there's one term in the sum for each isomorphism class of objects, and then you take 1 over the size of the automorphism group of that object. So again, this is a natural way to count objects in the presence of symmetry. So now let me have in mind the special case where Y is smooth of dimension D. So definition, in this situation, we'll say that Y satisfies the Grothendieck-Lefschetz trace formula if, well, the number of FQ points of Y is given by some formula involving the trace of Frobenius on cohomology. And here I'm stating it in maybe not the most common way. I'm stating it in a sort of Poincare dual form so that it will apply nicely in the case that I'm interested in. So this says that if you take the number of FQ valued points of Y and divide by your naive expectation for what that should be, Q to the dimension of Y, that this should be something which is all right as the trace of Frobenius inverse on the cohomology of Y bar. So here Y bar will mean Y crossed with the spectrum of the algebraic closure of FQ. And I'll use this notation throughout the lecture. I'll just put a bar on something to mean, oh, not on that. I'll put a bar on something to mean that I've extended scalars up to the algebraic closure of my field. Yeah?
Can you say what it means for a stack to be smooth at dimension D? You say Y is a stack yet?
Y is an algebraic stack, which means that it's locally an algebraic variety. It admits a submersive map from an algebraic variety. And smooth means that that algebraic variety is smooth.
Thank you.
Okay, so you can then talk about the L-adic cohomology of Y bar. This is some vector space over QL with some automorphism called the Frobenius. And you can contemplate the trace of the inverse Frobenius, which by definition means you take the alternating sum of the trace of Frobenius inverse on the individual cohomology groups. And so if this trace actually gives you the number of FQ points of Y divided by Q to the D, then we'll say Y satisfies the Grothendieck-Lefschetz trace formula. So for example, the classical Grothendieck-Lefschetz trace formula tells you that this is true if Y is an algebraic variety. But we would like, for applications to phase conjecture, to apply the Grothendieck-Lefschetz trace formula in the case where Y is a stack, like the moduli stack of G bundles on X. And what I would like to do in this lecture is just talk about a baby version of that. I would like to talk about what the Grothendieck-Lefschetz trace formula says for something like a moduli stack of G bundles, not on a curve, but just on a point. So an example is that we could take G to be now a linear algebraic group over the field FQ. And I'm going to take Y to be what's called the classifying stack of G. So what that means is that giving an R-valued point of Y is the same data as giving a principal G bundle on spec R. So here R is any FQ algebra. This is essentially the definition of what it means to be BG in algebraic geometry. So let's do an even more specific example. I'm going to take G to be the multiplicative group. So I'm going to take Y to be the classifying stack of the multiplicative group. That means that an R-valued point of Y is just an invertible R module. And so what is Y of FQ? This is the category of one-dimensional vector spaces over FQ. So we know what one-dimensional vector spaces over FQ look like. They look like FQ. So up to isomorphism, there's only one object in this category, but it has some symmetries, right? One-dimensional vector space has an automorphism group, which is the group of units in FQ. So if you count the size of Y of FQ in the sense that I defined earlier, well, there's one term that appears in this sum, and the denominator that appears is Q minus 1. So this is 1 over Q minus 1. On the other hand, what is this dimension of the moduli stack of BG in this case? So D, dimension of BGM. Well, you're supposed to think of BGM as what you get when you take the point, meaning spec FQ, and divide by the action of GM, divide by the trivial action of GM. So BGM is quotient of a point by the action of GM, or some people sometimes write this with a double slash to mean that they're taking the quotient in the world of algebraic stacks and not in the world of algebraic varieties. And so the dimension of BGM in this case is the dimension of the variety that's being acted on. In this case, it's just a point, so it would be 0 minus the dimension of the group that's acting, which in this case would be minus 1. So if I was to take the size of Y of FQ divided by Q to the dimension of Y, that expression that appears here, well, Q to the dimension of Y is Q inverse, and the size of Y of FQ is 1 over Q minus 1. So if I move the denominators around, I get Q minus 1 over Q. So now the Grothendieck-Lefschetz trace formula in this case is the left-hand side which appears in that formula. Let's talk now about the right-hand side. So right-hand side of the trace formula would be this trace of Frobenius inverse on the cohomology of the classifying stack of the multiplicative group. And I'll put a bar here to remind you we're over the algebraic closure of FQ. So let's talk not about what this would look like over a field of characteristic P. Let's first talk about what this would look like over the complex numbers. So the multiplicative group makes sense as an algebraic group over the complex numbers. And over the complex numbers, you can dispense with thinking about L-adic cohomology. You can actually extract honest topological spaces and just think about their cohomology in the usual sense of algebraic topology. So if you look at the complex points of GM, that's of course just the unit complex, the non-zero complex numbers. So it looks like the complex plane with the origin removed, and that's a group. And now the classifying stack of the complex numbers has an analog also in topology, which is what's called the classifying space of this group. I'll write it as BC star. So this is the group that, or this is a space that you get by taking the quotient of a contractible space by a free action of the group C star. It's well defined up to homotopy equivalence. So where would you find such a contractible space? Well, it's easy to find things with an action of C star. Right? You could take any complex vector space V. If V is a complex vector space, then of course C star will act on V by multiplication. Now that action won't be free. There's a fixed point, right? The element 0 in V. But if I take out 0, then C star is acting freely on V minus 0. Now if V has dimension n, then V minus 0 is homotopy equivalent to a sphere of dimension 2n minus 1. So V, before you remove the origin, is a contractible space, but after you remove the origin, it's no longer contractible. It now has this cycle of enclosing 0. At least that's what happens when V has dimension n, which is less than infinity. But if you took an infinite dimensional complex vector space, then removing the origin actually doesn't change its homotopy type. So if the dimension of V is infinity, then actually V minus the origin is still contractible. And then it's a contractible space with a free action of C star, and so BC star, this space which is well defined up to homotopy equivalence, might as well be what you get by taking V minus 0 and dividing out by the action of C star. And well, this space has a name. This is CP infinity. It's projective space over the complex numbers of infinite dimension. And now the cohomology of CP infinity is a calculation that is probably familiar to you if you've ever taken an algebraic topology class. So the cohomology with coefficients in some ring A just looks like a polynomial ring in one variable over A, where the degree of that variable is equal to 2. So that's what this cohomology looks like in the setting of ordinary topology. And in algebraic geometry, it works exactly the same way. So if you take now the L-adic cohomology of the classifying stack of GM over any algebraically closed field in which L is not 0, then what it looks like is, well, we're doing L-adic cohomology, so it's going to be a QL algebra, and it's a polynomial ring on one generator, T, where the degree of T is equal to 2. So now, or I should put a bar here, over an algebraically closed field. But now GM, if we're think of that as starting life over a finite field, there's some Frobenius that acts on this cohomology ring. And how does it act? Well, it acts by taking this generator T and multiplying it by Q. And it's a ring homomorphism, so it multiplies T to the n by Q to the n. So then what happens when you take the trace of phi inverse on the cohomology of BGM? Well, this is a sum. All the cohomologies in even degrees, so there's no signs. And what I see is just in degree 2n, I have to take the trace of multiplication by q to the minus n. So this is a sum of over all n greater than or equal to 0 of q to the minus n. This is a geometric series, and you can add it up, and you get q divided by q minus 1, which is exactly what you wanted to get. But because that was also the left-hand side of the Grothendieck-Lefschetz trace formula. So the conclusion is that the Grothendieck-Lefschetz trace formula is okay for this classifying stack BGM, even though it's not an algebraic variety. It's okay as long as you formulate it the way that we did over here. So in this maybe unusual looking form where we're thinking about the trace of the inverse Frobenius on cohomology, note that here you don't want to be thinking about the trace of Frobenius on cohomology, because now taking this trace involves an infinite sum. Something has to converge, and here trace of Frobenius inverse converges because the eigenvalues of Frobenius are like positive powers of Q. If you took the trace of Frobenius, it would not yield a convergent sum. Okay, so what I would like to do is tell you a different way of thinking about what you're doing here, a different way of thinking about this calculation. Another way of describing what I'm about to talk about is I want to teach you how to compute the number of points on things like algebraic varieties and algebraic stacks, not by thinking about L-adic cohomology, but instead by thinking about L-adic homotopy groups. So let me say a few words about this. So what follows, so y bar is going to be some algebra geometric object over an algebraically closed field K, and the case that I'm interested in is where K is the algebraic closure of a finite field, but it's not going to matter until later. And I'm going to fix a base point. So y is going to be a k point of y bar. So to this data, you can associate what's called the étale fundamental group of y bar with base point y. So this is a profinite group which was introduced by Grothendieck. It plays the role of fundamental group in algebraic geometry. So it's a profinite group which has a couple of characterizations, but one way of describing it is, let's say, let me assume for simplicity that y bar is connected. Then this profinite group is characterized by the fact that finite étale covers of y bar can be identified with finite sets with a continuous action of this étale fundamental group. So it's actually characterized by this property. There's a machine where you input a category that resembles the category of finite étale covers of y bar, and it outputs for you a profinite group that makes this statement true. And the étale fundamental group is defined to be the output of that machine in this example. So this is an invariant that was introduced by Grothendieck. Sometime later, a generalization of this invariant was introduced by Artin and Maser. Well, actually, before I do that, let me introduce a little modification. So this fundamental group, I don't want to deal with the entire fundamental group, because if you're in characteristic P and you look at the sort of, if you don't invert P in some sense, then you'll typically get invariants that are much larger than the invariants that you want. So I want to take étale fundamental group, and I'm going to write as subscript L to mean that this is the maximal pro-L quotient of the entire étale fundamental group. So it's a profinite L group, and here L is, as always, going to be some prime number which is not equal to 0 in the field K. So now, Artin and Mazur introduced a refinement of this étale homotopy group, something that they called the étale homotopy type of X. So to y bar, they associate. Well, there's a couple of ways of saying it, but I'm just going to say an actual topological space. Well, let's call it, I'll call it Z, with the following properties. Well, let me first say that what I'm describing is like the L-adic version of the Artin Mazur construction. So let me, I should add some assumptions that I'm going to make about Y now. So what I would like to do, I'd like to put myself in a situation where the space that they build is going to have good finiteness properties. So I can ensure this. I'm first going to assume that this Y bar behaves like it's simply connected, at least at the prime L. So this étale fundamental, L-adic étale fundamental group that I mentioned earlier, I want it to be 0. And another, that's equivalent to saying something simpler, which is that the étale cohomology of Y bar with coefficients in Z mod L is equal to 0 in degree 1. And I also want to assume that in every other degree, well, maybe not, étale cohomology with Z mod L coefficients is not 0, but I want to assume that it's finite. Finite dimensional as a vector space over Z mod L. So these are some finiteness conditions, the second of which would always be satisfied, for example, if Y bar was an algebraic variety. Okay. So under these assumptions, what Artin and Mazur produce is something that you can describe pretty concretely, or at least you can think about pretty concretely. You can think that their output is a topological space Z with two features. So first is that Z behaves like it's L-adically complete. So let's say Z is simply connected. And the homotopy groups of Z, pi n of Z, each homotopy group is a finitely generated ZL module. For every integer n. And the second thing that you want is that it's somehow related to Y bar. And the relationship is that if you compute the cohomology of Z with, let's say, Z mod L coefficients, and here I just mean the cohomology in the world of topological spaces. So the singular cohomology of Z with Z mod L coefficients should be the same as the étale cohomology of Y bar with Z mod L coefficients. So it's, if you think of étale cohomology as some way of making sense of invariants like singular cohomology in algebraic geometry, in cases where singular cohomology literally doesn't, would not be a sensible thing to do, this is, the Artin Mazur construction is something which elaborates on that. It says, you know, the étale cohomology of Y, it literally is the cohomology of another topological space that you can construct which is related to Y. And the virtue of that is that, you know, in algebraic topology, we're interested in all kinds of invariants of topological spaces, not just cohomology with mod L coefficients. And now, if you can apply this construction, you can now make sense of all kinds of additional invariants of an algebraic variety Y bar just by first producing this topological space Z and then applying those invariants to Z. So here I haven't defined what the étale homotopy type of Z is, or let me just mention, that's the terminology. Z is the L-adic homotopy type of Y. but it's morally characterized by these two properties. What I mean by that, it's not literally characterized by property 2. Property 2, as I stated it, is just saying there's an abstract isomorphism between two vector spaces. But property 2 should really be made more precise by saying that there's some datum that relates z and y bar, which induces this isomorphism on a tall cohomology. And if I was to say that carefully, this would become a characterization of what it means to be the tall homotopy type of y.
Question about this?
Yeah.
Actually, me. So you wrote Z, where you wrote this comparison with Z mod L. I mean, would you get the same thing if you took Z mod some power of L?
Yeah.
With the same space?
Yeah.
Okay.
Yeah.
So it captures all of those.
It captures all, I mean, like a map of topological spaces induces an isomorphism on cohomology with coefficients, Z mod L coefficients, if and only if it does the same for Z mod L to the n coefficients for all n. Yeah. Okay, so what does this let me do? Well, now for each n, let's say greater than 0, I can talk about pi n of y bar. And what I'm just going to mean is take pi n of this topological space Z. And so here maybe I should mention base points, although I'm in this case where these objects really behave like they're simply connected, so their homotopy groups are independent of a choice of base point. So this, by what I told you about Z, property 1, this is actually a finitely generated ZL module. And I'm going to, for this lecture, I'm just going to be interested in its rationalization. So this is what you get when you take pi n of y bar and then invert L. So this is now a finite dimensional vector space over QL. Okay, so my guess would be that there's a lot of people in the audience for whom L-adic cohomology is something familiar, and these L-adic homotopy groups are not at all familiar. So the first thing I would like to do is say something about how they're related to one another. So in ordinary topology, there's a relationship between homotopy groups and cohomology groups. There's a map from the homotopy groups of a space to the homology groups of a space called the Hurewicz maps. And homology is canonically dual to cohomology. I can think of the Hurewicz map as giving me some kind of a bilinear pairing between the homotopy groups of a space and the cohomology groups of a space. And we have the same thing here. So there's a canonical pairing, I'll write it as B, from pi n of y bar with QL coefficients cross hn of y bar. This is L-adic cohomology into QL. And how should you think about this? Well, these invariants are the same as the invariants that you would get by taking the usual singular cohomology of the topological space, Z. And if you think about this in the world of honest topology, an element in pi n of y bar is represented by a map from F, from an n sphere into this space Z. And maybe you have some cohomology class, eta, living in the cohomology of y bar with QL coefficients, which is the cohomology of Z with QL coefficients. And then what you're supposed to do is just take the pullback of eta. And, well, let's say B of F comma eta is the pullback of eta, which lives in Hn of the n sphere with QL coefficients, which is canonically isomorphic to QL itself. Sorry? I can't hear you.
Is
Sure, sure. Okay, so what can I say about this pairing? Well, first, this pairing is only interesting when n is greater than 0, because in degree 0, there's no homotopy group of y. So let I be the reduced cohomology of y bar. So this just means the sum of hn of y bar where n is greater than 0. I want to think of this as an ideal sitting inside the entire cohomology ring of y bar. And so note, let me think of this pairing then as a pairing between pi star of y bar cross I into QL. And the claim is that this descends to a pairing, which I'm also going to denote by B, from pi star of y QL cross I mod I squared into QL. In other words, the pairing that I defined earlier, it automatically vanishes on any cohomology class that you can decompose as a product of two cohomology classes of lower degree. And that's just comes from the formula, or comes from the observation, that if eta is a cohomology class that you can write as a product of eta prime times eta double prime, where these are of smaller degree, and F is a map from a sphere into Z, then the pullback of eta will also factor as a product of two cohomology classes of smaller degree. But now that's an equation which is happening in the cohomology ring of a sphere. And the cohomology ring of a sphere is not very interesting. The cohomology of a sphere vanishes in all degrees strictly between 0 and n. And so these two factors would have to vanish. Okay, so this is a relationship between the homotopy groups of y bar and the cohomology of y bar. And now, in some cases, this is all there is to the story. So, well, assertion, it's really just a fact of topology, which I'm applying to this particular situation, is that if you were in a situation where the cohomology ring of y bar is a polynomial ring on generators of even degree, then this B, I mean the latest B, maybe I should call this B bar to distinguish it from the first B, this is a perfect pairing. And what that means is that if these L-adic homotopy groups are something that you can just read off of the cohomology. They're just the dual of I mod I squared. And on the other hand, the cohomology is almost something that you can read off of the L-adic homotopy groups because the cohomology ring H star of y bar has this I-adic filtration and so forth. And if it's a polynomial ring, this will be an exhaustive filtration, and the successive quotients will be something that you can read off of the L-adic homotopy groups. Now, if you're thinking y bar is something like an algebraic variety, then this doesn't sound like a very plausible scenario, right? The cohomology ring of an algebraic variety, the cohomology groups are concentrated in degrees 0 up to twice the dimension of the variety. So it can never look like a polynomial ring on even generators. But if y bar is allowed to be something like an algebraic stack, it's possible for the cohomology of y bar to behave like this. And in fact, we already saw an example. If y bar is the classifying stack of GM, then this applies. In that case, we saw that the cohomology ring was a polynomial ring on one generator in degree 2. So let's just think about what the Grothendieck-Lefschetz trace formula would be saying in this special case where the cohomology of y bar is a polynomial ring. So suppose that the cohomology of y bar is a polynomial ring, and I'm in the situation where y bar is obtained from something that's defined over a finite field spec FQ. So in that case, y bar is equipped with this geometric Frobenius map, which induces an automorphism both on its L-adic cohomology and on its L-adic homotopy groups. And this pairing is equivariant with respect to the action of Frobenius. So now the Grothendieck-Lefschetz trace formula asks you to compute, or involves the computation of the trace of Frobenius inverse on the L-adic cohomology of y bar. So maybe I should say a few words. What does this actually mean when it now involves an infinite sum? Well, to make sense of that infinite sum, what you should do is fix an embedding of QL into the complex numbers, and then what you're supposed to do is, you're supposed to take some alternating sum of minus 1 to the I, trace of Frobenius inverse on HI of y bar. You think of this as a finite dimensional vector space over QL, then taking the trace gives you an element of QL, which you then use this embedding to think of as a complex number, and this infinite sum you're supposed to make sense of using the usual topology on the complex numbers. That's what we did in the example of BGM. We took that geometric series, 1 plus Q inverse plus Q to the minus 2 and so forth. That converges for the usual complex topology. Okay, so what can we do in this case? Well, now I want to I'm in this situation where the cohomology of y is a polynomial ring on even generators, so this quotient I mod I squared is now a finite dimensional vector space over QL. So pi star of y bar, QL, this I said is now the dual of I mod I squared, and this is finite dimensional as a vector space over QL and concentrated in even degrees. So now let me think about the eigenvalues of Frobenius on this once I extend scalars to the complex numbers. So the Frobenius has complex eigenvalues, which I'll denote by lambda 1, lambda 2, and so forth, lambda n. So these are counted with their multiplicity as generalized eigenvalues for that linear operator. Okay, so these are the eigenvalues of Frobenius on pi star of y bar QL. And therefore, the Frobenius inverse has the same complex eigenvalues on the dual of pi star y bar, which is what I mod I squared. Now, what about Frobenius acting on this cohomology ring of y bar? What does that look like? Well, we have this I-adic filtration of the cohomology of y bar, and trace is additive for exact sequences. So if I want the trace of Frobenius on this entire cohomology ring, that's the same as the trace of Frobenius on the associated graded of that cohomology ring with respect to its I-adic filtration. And therefore, it's the trace of Frobenius inverse on the symmetric algebra of I mod I squared. And if we know what the eigenvalues of Frobenius inverse are on I mod I squared, then we know what the eigenvalues will be on the symmetric algebra on I mod I squared. So this is the eigenvalues of Frobenius inverse on this symmetric algebra are just monomials that you can write down using lambda 1 through lambda n. So let me just write that. Trace of Frobenius inverse on sim star I mod I squared would be the sum over all integers, let's say e1, e2, dot, 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 through en greater than or equal to 0, lambda 1 to the e1, lambda 2 to the e2, and so forth, lambda n to the en. And while this is a sum that you can evaluate, it's now a product of geometric series. So this, some elementary manipulations will tell you this is the product as I goes from 1 to n of 1 over 1 minus lambda I. But now, what are these lambda i's? Again, they're the eigenvalues of Frobenius inverse on the homotopy groups, the L-adic homotopy groups of y bar. So let me just rewrite the conclusion of this calculation. The trace of Frobenius inverse on the cohomology of y bar is, well, now I'm expressing it as a product. So let me first take the inverse of this to get something that I can write more simply, and then what I'm looking at is the determinant of 1 minus the Frobenius acting on this now finite dimensional vector space, which is pi star of y bar over QL. Okay, so let's just check, let's do a reality check. We computed this earlier in the case of GM. So, or sorry, when the y bar is BGM. So in that case, we had a polynomial ring on one generator as the cohomology. So this homotopy groups is just going to be a one-dimensional vector space. Vector space which is concentrated in degree 2. And how does the Frobenius act on this one-dimensional vector space? Well, it acts by the dual of the way that it acts on cohomology. So Frobenius actually acts by multiplication by 1 over Q. And so this determinant of 1 minus the Frobenius is actually just 1 minus 1 over Q. And when you take the inverse of that, you get Q divided by Q minus 1, which is the same thing that we got earlier. Okay, so this is what happens when the cohomology ring of Y is a polynomial ring. And that doesn't happen for algebraic varieties, but it does happen for certain algebraic stacks, including the ones that I mentioned earlier in this lecture. So now let G be any linear algebraic group. Over the finite field FQ. And let's see what the Grothendieck-Lefschetz trace formula would say about G. Sorry, not about G, for the classifying stack BG. So what does it say? Well, on the left-hand side, we would have the number of FQ points of BG counted with multiplicity. Yeah? No. What's that? They're in even degrees. Okay, so first, maybe I should mention, if G is a linear algebraic group over FQ, and you look at the cohomology of the classifying stack BG, that always turns out to be a polynomial ring on even generators. So it's a situation to which our analysis here applies. And let's see what the Grothendieck-Lefschetz trace formula translates to using this analysis. So the left-hand side, remember, something like the number of FQ points of BG divided by your back-of-the-envelope estimate for what that should be. And you're asking whether or not that's equal to the trace of Frobenius inverse on the cohomology of, sorry, not Bungie, BG. Okay, so now we can evaluate the left-hand side, because if G is, well, now let's say a connected linear algebraic group, then there's only one principal G bundle on spec FQ by a theorem of Lang. Every principal G bundle for a finite field is automatically trivial, and the trivial bundle has automorphism group given by the finite group G of FQ. So the numerator here is 1 over the size of G of FQ, and the denominator is, again, your naive estimate for that. It's 1 over Q to the dimension of G. So we could rewrite this as earlier, moving that expression up to the numerator and the size of this finite group down to the denominator. Okay, and now what about the right-hand side? Well, the right-hand side is something that we just computed in terms of the action of Frobenius on the homotopy groups of BG. So this can also be written as, there's an inverse here, but the determinant of 1 minus Frobenius on the homotopy groups of Y bar with QL coefficients. And so if you clear some denominators, what this is giving you is a formula for the number of FQ points of G. This is equivalent to saying that the number of FQ points of G is Q to the dimension of G, that's your naive estimate for how many FQ points there should be, times a correction factor. And that correction factor is the determinant of 1 minus the Frobenius on the homotopy groups of BG. And this is called Steinberg's formula. It's not phrased by Steinberg in terms of L-adic homotopy groups, but there's many equivalent ways of stating what vector space, many equivalent ways of describing what vector space that you're taking the determinant of 1 minus the Frobenius on. So let's just, we've done this in the example of the multiplicative group. Let's do it in a slightly more complicated example of GLN for some integer n. So example, take G to be GLN. So in that case, the cohomology ring of BG, well, first, what is BG in this case? BG is the classifying stack for vector bundles of rank n. And the cohomology ring looks like a polynomial ring on generators in degree 2, 4, 6, and so forth, up to 2n. Those generators look like, can be identified with the Chern classes of the universal vector bundle of degree n. It's a polynomial ring on generators C1, C2 through Cn. And therefore, if you look at the homotopy groups, BG bar with QL coefficients, what this is going to look like is it's a vector space of dimension n over QL, where your generators are in graded degrees 2, 4, 6, again through 2n. So let's say this is the QL vector space generated by classes E1, E2, and so forth through En that are kind of dual to these Chern classes, C1 through Cn. And now how does the Frobenius act? Well, the Frobenius acts on these Chern classes by multiplying each, well, Ci by Q to the I. And therefore, the Frobenius acts on these homotopy groups via the sort of dual formula that on each EI, it will divide it by Q to the I, Q to the minus I times EI. So then what does Steinberg's formula say? So it says that the number of elements of GLN FQ should be, well, first, Q to the power the dimension of GLN, that's n squared. And then I have to multiply by this correction, which is the determinant of 1 minus Frobenius on this n-dimensional vector space, and that's just a product of n factors where I have 1 minus the eigenvalue that Frobenius is acting in each graded piece. So we have a 1 minus 1 over q times a 1 minus 1 over q squared times a dot, 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 1 minus 1 over q to the n. And I will leave it to you to check that that formula is correct. Oh man. So I am supposed to stop now, or? All right. I'll just go on a little bit longer. Okay, so this is a story that I've so far told under the assumption that the cohomology ring of Y bar is a polynomial ring. But that's pretty rare. It's not true. It's never true for an algebraic variety, which is more than 1 point. Now, if the cohomology ring of Y bar is not a polynomial ring, the relationship between the L-adic cohomology of Y bar and the L-adic homotopy groups of Y bar is a little more complicated. You can't just read one off from the other. But they are still related. And so let me say, in general, meaning not assuming that the cohomology of Y bar is polynomial, the relationship can be described by a spectral sequence. There's a spectral sequence where you start with the symmetric algebra on the dual. You take the L-adic homotopy groups of Y bar and dualize them and take the symmetric algebra. And this is the E2 page of your spectral sequence. And at the end, you get some filtration. You get the associated graded for some filtration on the L-adic cohomology of Y bar. And the case where the cohomology of Y bar is a polynomial ring is the case where this spectral sequence degenerates. The E2 page and the E infinity page are the same, and in that case, this symmetric algebra just is the associated graded of a cohomology of Y bar. So in general, there's a spectral sequence, and some things might happen in this spectral sequence. In fact, some things must happen in this spectral sequence if the cohomology ring of Y bar is not polynomial. But if you're just interested in computing numbers, like the trace of Frobenius on something, it doesn't really matter if something happens in this spectral sequence. The trace of Frobenius on the E2 page of this spectral sequence will be the same as its trace on the E3 page, same as its trace on the E4 page, and so forth, and you actually get exactly the same conclusion. So this gives the existence of this spectral sequence, this gives the same conclusion that the trace of Frobenius, Frobenius inverse on the cohomology of Y bar is the inverse of the determinant of 1 minus the Frobenius on pi star of Y bar. So now I should be a little bit careful about even degrees versus odd degrees. These homotopy groups might not be concentrated in even degrees anymore, so I should really write this as a product over all I of the determinant of 1 minus Frobenius on pi I of Y bar raised to the power minus 1 to the I plus 1. That's just what this expression means. So you get the same conclusion. Let me be a little careful here. You can get the same conclusion formally. You can just play games with infinite sums, and it looks like this should be true. So let me add, assuming everything converges. And when does everything converge? Well, one way to ensure that is, for example, if you knew that these homotopy groups were finite dimensional as a vector space. I mean, they're automatically finite dimensional in each degree under the assumptions that I mentioned earlier, and if they're concentrated in finitely many degrees, then everything will converge and you will get this conclusion. And therefore, you'll be able to compute, well, therefore the growth and Dieck-Lefschetz trace formula will be equivalent to something that you can state in terms of this determinant of 1 minus Frobenius on pi star of y. So let me just conclude by advertising what's the point of this. I'll get into it in the next lecture. This will apply when y is Bun gx. So I'll elaborate on this next time. Thank you very much.
Questions?
So for the Archimedes construction, can you also do the same thing for L equals to P?
You can also do the same thing when L is equal to P, but you will get something that maybe you didn't want.
This is very basic question. In the spectral sequence, which is P and which is Q? And first, if if the E to PQ is that, which is P and which is Q?
Sorry, I didn't understand.
About the numbering of the spectral sequence.
Yeah.
Oh.
E2PQ.
Right, so that, so pi star of y is already a graded vector space. So when I take the symmetric algebra on that, that has a natural grading, and it has a second grading given by the degree inside the symmetric algebra. And those are the P's and Q's.
Thank you.
Is the spectral sequence a purely algebraic topological result?
Yeah. Yeah, there's a spectral sequence like this in topology, and you can more or less just export it to.
Further questions?
So I'm curious, when you told us how to compute the cohomology of BGM, and you sort of explained the topological side, and then you said it's the same on the étale side, is that a consequence of the topological statement? Do we have theorems that are good enough to carry over the computation from the complex numbers to the L-adics, or are you doing a separate computation of BGM on the L-adic
I
side?
mean, if you were interested in fields of characteristic zero, then I think it's sort of formal because of comparisons. You know, Lefschetz's principle will reduce you to the complex numbers, and then you have comparison theorems there. I don't think it's completely formal that it works out the same way in characteristic P as long as you're talking about L-adic cohomology for L different from P. For example, it doesn't if L is equal to P.
Right, but I had in mind characteristic P, L different from P, yeah.
Yeah. I mean, I think you have to, input a little more.
Gotcha.
So for a given group G, you would have the cohomology of BG would be a Hopf algebra, right?
The cohomology of BG?
Yeah.
No, I mean, if G is commutative, it has a Hopf algebra structure.
Commutative, okay. So in
I mean,
which
the
cases
cohomology of
would
G
you-
has a Hopf algebra structure, but not BG.
Okay. So in which cases can we expect polynomial structure for the cohomology of BG?
I mean, I wouldn't expect that it happens in too many more examples. I mean,
Okay.
these are some very special examples.
Thanks.
Okay, let's take a very short break and resume again in about 5 minutes.